He's an alumnus of IIT Kanpur and got his PhD from University of Maryland. He then had stopovers at Princeton and Virginia Tech before finally landing up in Arizona. His research interests are broadly in information theory and its applications to a wide variety of domains, including wireless networks, security, privacy, and machine learning, and he's going to talk to us about differential.
Thank you so much. Thank you for arranging this in the chat, and very nice to talk about right away. I think it's on. So today I'm going to talk about work on differentially private community detection, more stochastic block models. It's a joint work with former student of mine, Mohamed Seif, who is a postdoc at Princeton, and Dung from University of Virginia, and Anil, who is a faculty at University of Virginia. So here's a quick outline of the talk. So I'll start with giving you a very brief overview of what I mean by community detection. Some of you may have worked on it, so this will be known stuff for some of you, but I'll try to keep it a little bit tutorial in content and a little bit of what we have done towards the end of the talk. Then I'll tell you a little bit about stochastic block models, differential privacy over graphs, and then some of our recent work on differential privacy for stochastic block models. Am I audible? Alright, so we know networks are everywhere and come in different variety of applications and scenarios, including biological networks, where we see how different communities interact with each other, what the interplay between features of one community versus another, and how violence propagate, things propagate, or genetics propagates. Of course, for youngsters, social networks are the network. People study how information propagates over social networks, how groups form, and so on. And then there are, of course, collaboration networks, researchers and faculty members who collaborates with whom. And then contact tracing networks, these begin the networks to study. So what do I mean by community detection in networks? Very broadly speaking, when I say network, I'm going to talk about a graph. The graph will have nodes, edges. For us, to on the top, nodes will correspond to individuals or people, and edges will correspond to relationships between people. For example, it could correspond to two people connected on Facebook, corresponding to a social network as a mind, or it could be proximity or contact between two people who came in close contact with each other when you're thinking about a contact tracing network. And nodes in general could be with or without attributes. So it could be just a plain node corresponding to an individual, or it could be a node with an embedded long vector associated with it, where it could be more information, more richer structure. So this talk, for simplicity, I'll just focus on without attributes. So what do we mean by community detection? Roughly speaking, it corresponds to the problem of identifying groups or clusters that are alike or similar from similarity relationships. So if two people or two groups of people like similar things, then they will be clustered in a similar group, and then they will have it. As you can imagine, what is the mathematical definition of community? There is no single standard definition because it's a subjective notion, and it very much depends on the underlying problem and application. In many applications, there are a variety of applications of community detection. Targeted companies like Facebook and others always strive to do targeted marketing, make more impact for the marketing revenue that they get, and make their clients more happier. For social media, in epidemiological analysis, identify clusters and outbreaks. In genetics, people use these kind of networks to identify similar subpopulations to different treatment effects and so on. And of course, in image segmentation, signal processing, so any questions so far? Please feel free to stop me. So how do we go about detecting whether a network has communities? How can we cluster a graph into different communities? So So there are sort of three broad approaches to do clustering or community detection. The first broad approach is hierarchical clustering, which you can think of this as an agglomerative approach, where you start from small number of nodes and you slowly build a cluster, putting nodes which have similar properties in the cluster. So you maybe start with a few seeds and then you sort of build around the seeds and then you come in a hierarchical way and come up with a bigger. And depending on how you formulate your objective or cost function, different hierarchical methods lead to different communities and potentially different utility tradeoffs. Okay. Excuse me. And then there are statistical methods which sort of assume that there is a generative model for the underlying graph, and then find clusters that best explain the graph. So they assume that the graph is coming from or drawn from some underlying probability distribution, and then you write down, let's say, the likelihood function, and then find the best cluster that explains the likelihood function. Okay. Now this talk is going to follow this vertical, that is statistical methods, and focus on one very, very specific model, a generative model called stochastic model. I'll explain that. Okay. Now this is, as I said, this is a very basic fundamental model, and then there are more, bells and whistles you can add to it and make it more richer, removing some of the shortcomings in the elementary features. There are degree corrected SBMs, graph forms, attributed models, and so on. But scope of the talk, I'll just focus on the simplest. And then there are other methods like cost and score-based methods that they want to partition a graph into communities which minimize a certain cost, and the cost is specified a priori to the clustering algorithm, and then given that cost you try to find the best cluster you can find. Okay. So for example, there are modularity-based clustering algorithms, there is minimum cut-based algorithm, and so on. So there is this problem of community detection clustering is very rich history. That's what I want to highlight and give you a very sort of quick overview of the type. So why should we care about statistical methods, or specifically like these generative models and doing clustering of generative models? So first of all, it's a fertile ground to analyze clustering algorithms. Once you assume that underlying graph is coming from a certain distribution, then you come up with your favorite algorithm, your clever algorithm for clustering. You can analyze, hopefully try to analyze that algorithm and see how well you did. Okay. Are you truly recovering the underlying communities that the graph was drawn from? There are interesting fundamental barriers, information-theoretic barriers, as to when can you cluster and can you not cluster, and I'll talk about that in a second. And there is of course interesting interplay with statistical and computational questions. So we will see in a second that some of these questions lead to computationally hard problems. So we can't necessarily hope to solve them in the worst case unless solve equal to those kind of questions. But at least if we assume that the data or the graph in this case is drawn from a distribution in a distributional setting, we can still solve these problems close to what information theoretic extends. And more generally, I mean, these are fun things to do. So that's another information. Alright. So let me tell you about stochastic block models, what they are. I'm going to talk about the simplest model to keep things in perspective. So it's a random graph model. So I'm going to assume that I have a network with two communities. So two communities, I have n nodes. Each node has a label. Either it's a blue dot or a red dot. Okay, so I'm going to denote blue or red as +1 or -1. So sigma i's are always going to denote my labels. So think of +1 as one color, -1 as the other color. Okay. And the generative model is specified as follows. Given the labels, so first of all, I have, let's say I have these many, I don't know, 30 people in this room, so everybody is assigned a label uniformly at random, blue or red. Then once the labels are assigned, then two people who are in the same color, will be connected with the probability B, and people who are not of the same color will be connected with the probability Q. So that's how I'm going to draw this graph. So if sigma I is equal to sigma j, that is if people have the same color, then I is connected to j with probability p and not connected with probability p. If If they are not in the same community, then you are connected with the probability. It's natural to assume that since you have the same color with your friend in the same community, you should maybe be connected with higher probability. So we have these greater. Okay, so the rationale, as I said, is nodes within a community tend to be connected more compared to nodes across other communities. Okay. So there are three parameters in this model: n, the number of nodes; p is the inter-community connectivity probability, and q is the intra-community connectivity probability. Okay. So this SBM NPQ specifies this whole joint distribution of the graph of this model. This model was proposed back in the 80s, and you can, if people know about Perturbation graphs, it's a sort of a generalization from that. Perturbation graph is just a single community where nodes are connected with a certain probability p and not connected with a probability. Any questions about the model? That is fixed to half for now, yeah. But you can generalize this when there is a prior on how many nodes are blue and how many are red. So if let's say maybe 30% are red and 70% are blue, so you would put a prior on sigma i's. So you would each person would be red or blue with 70 and 30 likelihood, and then you would still maybe go ahead and draw them with a certain probability. Okay. So as I said, generalization exists to not just two communities, multiple communities. You could have asymmetric inter and intra-community probabilities and so on. So all those generalizations exist in computation. So what do you mean by recovery? So here is the core problem of community detection. We assume that we are given a graph which is drawn from this probability distribution. We know what is n, the number of nodes. We know p, we know q. Okay. And then all we are given is the skeleton of the graph. The goal is to label or color the graph and place nodes as red or blue. Okay, so that's the goal of community detection. Alright, so this picture looks nice and clean because I've already colored it. But what you get in reality is just a graph, and then you have to color the node, is this red or blue? Okay. So when you, let's say we come up with an algorithm and we color the nodes, some of them are red, some of them are blue, then we have to ask this question, how well have we colored the nodes? So that's what I mean by notions of community recovery, how well you are recovering the underlying colors. So there are two broad notions people study. The first notion is called weak recovery. So weak recovery says that the probability that, let's say, sigma hat I is the estimate of the label for the I. The probability sigma hat I is not equal to sigma star I is less than half minus some number x. So it's slightly better than I would guess. So this notion is known as weak or partially. The other notion is asymptotically exact recovery, sometimes called strong recovery in the literature. So this requires that the probability that the whole vector, sigma hat is the vector of labels that you get for all the n nodes, and sigma star is the underlying ground truth. The probability that this is not equal to the underlying ground truth vector goes to 0 asymptotically as the graph side goes, as n goes to 0. So it's not very hard to show that if this is true, then that is true, but not the other. Okay, so this is a strong notion. So what are the questions we want to study, or people try to study in community detection? They ask the question, when can we recover the underlying graph as a function of p and q? So remember, there are three parameters, n, p and q, which are fixed and known to us. So if, and we also assume p is greater than q, right? So suppose p is equal to q. P is equal to q means what? That whether you are in the same community or you are in a different community, you are connected to the same probability. And now I am showing you the graph and asking you to color the nodes. Is it possible to color the nodes? No, because whether you are in a community or not in the community, you are have a similar behavior with your community neighbors or outside. So ideally, it should be possible to recover when P is larger than Q. But how large should P be compared to Q? Okay, so that's the core question people ask. What's the sort of phase transition? That how large should P be in comparison to Q so that you can really recover the underlying probabilities. Okay. So you can ask the same question for either weak recovery or for exact recovery. Okay. And so So these are sort of statistical questions, and then we ask the corresponding computational question that, let's say, information-theoretic bounds tell us that if P is 2 times greater than Q, I'm just making that threshold up, then there exists some estimator which can recover the labels. Then you ask the question that, when I really realize this in practice, can I come up with an efficient way to estimate the labels? Okay. So these are sort of the 2-part questions we came about. Okay. So it turns out there are different sort of regimes in stochastic block model. Yes, yes. So the first requirement is that, yes, so this should hold for every node. So for every node, you should be better than the random case bias model. And for the other one, this is the whole vector. This is, so sigma hat is the whole vector of estimates, the n length vector. And sigma star is yet to be known.
Why is P plus Q not 1?
P plus Q doesn't have to be 1. So let's say I'm a Democrat, or let me see, use a different example. Let's say I'm a BJP supporter, and you are from a different party, from a different party. So I'm connected to another BJP supporter with probability 0.9, but I'm not connected to a non-BJP party supporter with probability 0.375. So these two probabilities do not need to add 1. So the what thing adds to 1? The probability I am connected to another BJP supporter with probability 0.9 and not connected with probability 0.1. So those two numbers add up to 1. But P and Q don't need to add up. Okay? Okay. So turns out there are different interesting regimes in SBM. So if suppose P and Q scale inversely proportional to n. So remember, n was the size of the graph. So if P behaves like some constant by n, Q scales as a constant b by n. So which means that the average degree of every node is constant. So if you think about it, what is the average degree? Average degree is the expected number of nodes a user is connected to. A user is connected to the same community with some probability and not in the same community with some probability. Since probability themselves is a by n, number of nodes is n. So n times p plus n times q will be a plus b, so which will be a constant. Right? So average degree will be a constant. And it turns out that in this regime, and this follows from classical analysis of order Schwenning graphs, that a fraction of nodes will be isolated with high probability. So if some of the nodes are sitting here alone, which are not connected to anybody, okay, and we have two communities, then what do we do with these? Who should we label them as? +1, -1, and -2. Okay. So it turns out in this case there is no hope of exact recovery. You can show that for those isolated nodes you are going to make an error always. So constant fraction of them you cannot recover the nodes, the labels exactly. But it is possible to do partial recovery or weak recovery. Right? So you can do still better than a random case. Okay. And so people have studied this problem of partial recovery and have shown that, the separation, they have studied the separation, minimum separation needed between P and Q to allow for decay. Okay. And in the dense regime, so why do I say dense? Because the average degree now P and Q now grow as A log n by n and Q as B log n by n. So you can imagine average degree now grows faster, grows logarithmically with n. In this case it turns out that there are no isolated nodes. So everybody is in some sense connected to at least one node in the whole graph. And then turns out there is hope of exact recovery, and people have studied this setting. So that's what I call as sparse regime and dense regime. So by sparse and dense I mean the average degrees of it. Okay. So again, none of this is my work. This is a slide which I lifted from Emmanuel Abe's talk on community detection. So this is a very nice survey paper by him. This is, I think, quite old now, 9 years old. There are many other subsequent works that, if you're interested in this, I think this is a very good starting point to learn about community detection. So people have studied various algorithms. So if you see, from the 80s all the way till in the previous decade, people looked at different algorithmic methods, min-cut spectral methods, EM algorithm, and so on and so forth, and try to analyze them, that how much separation would each algorithm need, how much separation between P and Q would each algorithm need for exact recovery. So as you go along the decades, you would see that the separation between P and Q was reduced. So algorithms would need smaller and smaller separation to still do recovery. So the smaller the separation, which means that you're doing a good job, and even closely related communities could be separate. Okay. Is that clear? Okay. Alright. And I think somewhere in the mid last decade, we actually figured out the exact threshold. So this was a work by Ravi's group and Mohamed Seif. I think there were two groups who independently exactly characterized the phase transition threshold. Right? What is the exact threshold? What is the exact difference between P and Q we need for community integration? Okay. So let me give you just a very quick algorithmic overview. So yeah. Correct. P to be large, correct. So you should be well connected with your neighbors. But if Q, let's say, grows sub-logarithmically with N, the problem probably becomes easier as well. Right? So it's probably harder when P and Q grow with the same asymptotic. So it turns out that if you write down the optimal maximum likelihood estimator, this is what it looks like. Okay. So remember, we have a graph drawn from this SBM and PQ. Okay. If you write down the probability of observing a adjacency matrix A given a fixed set of labels sigma. So this is just the likelihood function. Right? It turns out that this can be written as sigma transpose A sigma. So remember, A is the adjacency matrix. Now, A by throughout the top, and I will denote A as a 0, 1 adjacency matrix. Okay, 0 means no edge between two nodes, 1 means there is an edge. So the likelihood function is nothing but sigma transpose A sigma. So what is the maximum likelihood estimator? Find me the sigma that maximizes the likelihood function. So find me the sigma which maximizes sigma transpose A sigma, subject to a couple of constraints. The first constraint is that sigma I, each element of that sigma vector, should be either +1 or -1. Corresponding to one of the two communities. And for this case, I'm assuming that communities are exactly of the same size. So 1 transpose sigma must be sigma. Now, it's easy to write, but hard to solve. Turns out this is an LP problem related to one classical LP problem. So this is equivalent to minimum bisection problems in graph. So we can't really hope to solve it efficiently. But we are not working in the worst case. We are working for the case, we are looking at a scenario when the graph is drawn from a certain distribution. So at the very least, we can analyze the maximum likelihood estimator. And so this is what was done by Abe and group in Moselle in 2014. And they showed that you can analyze the maximum likelihood estimator and show that exact recovery is possible if and only if square root A minus square root B square root A minus square root B is greater than square root. Okay. So what I'm showing you here in this graph is this fundamental phase transition boundary. Okay. So what this shows is x-axis is A. So remember, P is A log n by n. Y-axis is B, Q is B log n by n. So you pick your favorite choice of A and B, which then describes the connectivity parameters. If your A and B are such that you are here, then no algorithm can recover the probabilities. Okay. Whereas if you're here, then you can recover the probabilities. Okay. So this line is nothing but square root A minus square root B is equal to square root A. Okay. Alright. So there's a very interesting information-theoretic threshold phenomenon that happens in this problem. And then it was also shown that you can do STP relaxation of the maximum likelihood estimator and then analyze the STP relaxation and show that it actually achieves recovery up to this threshold. Okay, so this was done by Bruce Hayek's group, and there were many follow-up ones. So finally, I can talk about differential privacy within this context. So this was a sort of an overview of community detection, stochastic model, and what people say when they mean community detection over SBM. Okay. So now I want to talk about privacy within this context. So as you can imagine, graphs contain sensitive information, social, romantic relationships, for instance, edges between people, between you or my family member, my friend, or my partner, or whatever. In financial networks, edges between two nodes would correspond to a financial transaction. You may want to learn classify nodes, but still not reveal whether there was a financial transaction between two nodes. And then, there could be other relationships. So key questions of interest are: what is a good notion of privacy for graphs? How to design privacy preserving algorithms for community detection? And what's the impact of privacy on the phase transition for community detection? So I'm going to first quickly introduce what do I mean by graph differential privacy. Should I move this side? That corner is the problem, but the problem is I have to click it. That's another problem. But I think I'm okay for now. Okay. So I'm going to talk about two notions of privacy: node and edge differential privacy. So the first notion is node differential privacy. So it requires or tries to hide the presence or absence of a node. Okay, so here is what I mean. So I don't know how many people know what is differential privacy or have heard about differential privacy. Some of you I know. Okay, so what is the input to the algorithm? Input to the algorithm is the graph, which is the adjacency matrix. Okay. And the algorithm outputs some set of labels. So I'm going to call sigma hat, which takes A as input and the output of my algorithm. Okay, sigma hat A. I say that my algorithm is private. Let's say perfect. So let's start with perfect privacy. What would it take for an algorithm to satisfy perfect privacy? If I take two graphs, A and A prime, which differ in a node. So let's think of this as a graph A and think of this as a graph A prime. So in A prime, I've taken this node and deleted it. By deleting, I mean I take this node away and also all the edges that this node was connected to. So I take this node away completely. If the probability that my algorithm, when it takes this graph as input and outputs a community label estimate, versus it takes this graph as input and gives the same guy sigma as the output, if these two probabilities were exactly the same, then I would say this algorithm is perfectly private. It should hold for every A and A prime that differ in node, not just this very specific vector A. Okay. So if this holds for every A and A prime that differ in one node, then I would say this is perfectly private. Okay. If you look at the ratio of these two probabilities, right, this is the log likelihood ratio, right? And what does differential privacy require in this context? It requires this likelihood ratio to be bounded. Log of this ratio, forget the delta for a second. So if the log of this ratio is less than epsilon, then we say it's epsilon differentially private, or epsilon node differentially private within the context of graphs. This, without the delta, sometimes it's a bit too stringent, so we add an additive term, delta, and then it's called approximate differential privacy. That's why it's called epsilon delta differential privacy. So that's the notion of node differential privacy. Yes, questions.
So here now when removing the nodes, this vector sigma hat, the A and sigma hat different lengths.
Correct. So they are still of different length, but I mean you can still output an estimate for that time. So we don't do node DP in the in our work, we actually do edge differential privacy. So node DP would not make too much sense if you really hide the presence and then also classify the community label. So we don't study node DP in our work. We actually study edge DP. So I think this was just to give you an overview of graph differential privacy as to two type of notions. But yeah, I agree with you that it won't make operational sense for the community detection problem. I agree with you. Yes. No. So this holds for every and A prime. So the same inequality will hold if I switch these guys as well. Right? So this looks asymmetric, but since it holds for every pair, it should also hold for when this guy is A prime and this is A. Correct? So every inequality actually comes in pairs. But I'm writing it here because I'm sort of saving a line here. I'm saying this holds for every pair A prime and A prime. Okay, so edge DP is what we focus on, at least in our work, so that we hide the presence or absence of an edge. Here A and A prime now differ in one edge as opposed to one node. And then we require these two probabilities to be established multiplicatively and additively. And epsilon and delta are the two leakage parameters. As you can imagine, edge DP is a weaker notion than node differential privacy. It's also a simple fact of hard to prove. So people have studied edge differential, graph differential privacy back in 2007. A bunch of different papers have come out. But not much has been said, especially on the community detection problem. Okay, so here is what our goal will be. To design estimators for community detection which have two goals. First is exact recovery. So we want to recover the communities as people were doing before. And at the same time, we also want our estimator to satisfy epsilon delta edge differential privacy. Okay, so these are the two goals. We want to design efficient and private mechanisms, and given P and Q and a privacy budget, namely epsilon and delta, we want to ask when is exact recovery possible. Okay, as I increase epsilon, maybe it becomes easier. And then you want to exactly quantify the phase transition boundary. Okay? And understand the impact on the phase transition. Any questions?
Question of what this edge actually corresponds to. So the algorithm gets the whole graph. The algorithm pops out communities, some labels. So from the output of the algorithm, I shouldn't be able to tell if two nodes, or let's say a blue and a red node, are connected. Is that
correct? That's exactly what you want to do. So
how is that a function of the algorithm? Assuming that the algorithm is going to put the very high probability to be the two labels.
Right.
How is that? How that is something that imposes on the algorithm? This is something that I should not be able to deduce whether or not two nodes are connected from the output of the algorithm.
From the output of the algorithm.
That's an algorithm problem.
That's an algorithm problem. That's not a property of the graph itself. That's a property of the algorithm. So maybe tell me your question again.
So I guess, so hypothetically, the algorithm just always gives the correct answer somehow.
Right.
Would I be able to deduce whether or not
whether two people were connected or not, right? So that itself is a different question in itself, that how much information is naturally leaked by a natural community recovery algorithm, right? So we didn't look at that question. We didn't try to practice. So in some sense, you can think of that as an attack. That let's say there is a community recovery algorithm which takes a graph and outputs whether you are red or blue, or +1 or -1. And then I would go about saying that, I'm just revealing the community labels. Why should this tell me anything about whether two people are connected or not? So I would then try to maybe attack this algorithm and try to see how much information is leaked about an edge. Right? Whether can I learn how much, with what likelihood can I learn whether there is an edge present or not present between two. So that in turn will depend on the underlying statistics of the graph. Right? In the worst case, I don't know what I can say, at least theoretically. So I mean,
Is there at the core, is there like an accuracy versus privacy trade-off?
correct.
So the algorithm should be quote unquote noisy enough
Exactly.
such that
So we will see how to add noise. I mean that's going to be my next slide, is to how to add noise. Okay. So that comes to the privacy toolkit. How do I add noise? So broadly speaking, so let's say you have a data set D. Again, I've written data set in quotes. It could mean many things to many people. You know, it could be a database, it could be a bunch of images. So you have to compute some function f of t, function of this data set, subject to epsilon comma delta differential privacy. So there are two broad approaches that people use. Either you do input perturbation or you do output perturbation. So what is input perturbation? You add noise to the data set itself. So for every entry you add noise itself. Somehow the amount of noise you add better satisfy your privacy budget in the privacy notion. Once you do that, then you are in some sense free of privacy constraints. You have a noisy data set, then you do whatever you want. Okay, so there is something called post-processing property of privacy. And then you compute the function f on perturb data. Of course, this is very general purpose. It's not adapted to the type of function f that you want to compute on the data set. So it leads to naturally oriented. The other method is output perturbation, which is more prevalent, which is compute f of d exactly on the original database and then perturb f of d and then release it. So there are two broad output perturbation mechanisms. The first one is additive noise mechanisms. So you take your function f, compute it on the database, or in this case our graph. So our database will be the graph in our problem. And then you add some noise to it. So the first question is how much noise and what type of noise and how much noise you add. Okay. So there are two broad, actually the main idea behind this adjacency. For our case, it will be the adjacency matrix. No. So if you perturb the input, then you will either take an edge and either keep it or remove it. That's going to be perturbation of the data set. Perturbation of output will be you will take your graph, run a community detection algorithm, you will get some output. So you get labels, you get the label vector, and then you're going to flip the label somehow. Okay. So those are the two sort of broad things within this context. Okay. So how much noise people add? People add noise which is proportional to the sensitivity of that function. Okay. So as you can imagine, if a function is very sensitive, quote unquote sensitive, what do you mean by sensitive? If I take a data set and remove an element or remove a row from it and see how much did the function change, with a row or without a row, and look at the worst case change in the function. If the function did not change too much, then in some sense the function itself is very private. It's not telling me whether a person participated or did not participate in the computation of f. Then I should not be needing to add too much noise. But if the function changes by a lot, in the worst case by addition or deletion of a row, then I better add noise, because that's what my goal was in the first place, or that was my sort of goal in the privacy notion. So noise is typically proportional to global sensitivity and then divided by epsilon, and then the parameters of this noise, depending on whether you are taking Laplacian noise or Gaussian noise, you pick the parameters accordingly. Now it turns out global sensitivity can be quite high for very simple graph problems. Give me a graph and you want to ask how many triangles are there in this graph. Very simple computational problem. The number of triangles, the sensitivity is sort of proportional to it. Okay. So the amount of noise will blow up for a very simple graph statistic. Okay. So there are other alternatives people have studied. I'm not going to talk about that, but just wanted to give you a very quick flavor of additive noise mechanisms are one of the most prevalent ones. Other type of mechanisms are sampling mechanisms, exponential mechanism, and experience, and I'm going to talk about this in a second. So skip this slide. So there is some prior work on differentially private community detection. It's not like we are the first ones to think of this problem. People have studied, Erdős-Renyi graphs and estimating parameters of Erdős-Renyi graphs subject to node primes. People have studied modularity-based community detection with edge-differential privacy, some gradient-based methods for community detection, and then they look at edge-differential privacy. Spectral methods people have studied in stochastic block model, and then they look at differentially private versions of this. But by and large, these are sort of specific problems, and there was no work, at least we know of before this one, which looked at privacy, efficiency, and phase transition impact of phase transition. So let me start with running way behind, but let me start with the simplest method first. So say this is my graph, okay, and so which means I am given an adjacency matrix A. What should I do? The simplest method is, let's flip the edges. Okay, if there is an edge, let me maybe delete the edge, or if there is no edge, let me add an edge with some probability and hope to achieve epsilon differential primes, which is edge differential privacy. Okay, let's see how good this idea is. So what I will do, I'm going to take each edge and either keep it or flip it with some probability. Okay. So I'm going to get a different matrix A tilde out of this, right? And I'm going to do this independent in an IID manner for each edge. Okay. I'm not going to do correlated flipping. I'm going to do complicated stuff, very simple mechanism. And then once I get this A tilde, this new adjacency matrix, I'm going to give this as input to your favorite community detection algorithm, and then I'm going to get an estimate out of this. This is a fundamental property of differential privacy, that if you achieve differential privacy at any point, after that, if you don't touch the raw data, you are robust to the post-processing. Okay. So let's see how bad this is, or how good it is. So it turns out to achieve epsilon differential privacy, here is what you need to do. So remember, Aij is the ij entry of this adjacency matrix. So if it's 0 or 1, so the two values, right? So you flip it with this probability, 1 by e raised to power epsilon plus 1, or you keep the same value of Aij with this probability. So as you can imagine, epsilon is my privacy budget. So as epsilon is small, if epsilon is small, or if epsilon is large, which means I allow larger leakage, then essentially I don't flip it with very high probability. It's monotonically decreasing in epsilon. So I get this leakage for small epsilon. Now suppose I and j are in the same group. Okay. I'm just going to give you a flavor of why this is not a good scheme. So this appears as the simplest scheme you would think of. Right? You get the matrix and flip the values of Aij. And we can, so this is just randomized response. So if people know about differential privacy, this is the simplest thing you would try, because A is 0, 1 value. And I would take each entry and I care about edge differential privacy, let me just flip them. So if Ij are in the same community, P probability that Aij is 0 is 1 minus P, and Aij is 1 is P. Hopefully everybody is with me on this. Now I have flipped this guy and gotten a new matrix A tilde. Let's look at the probability A tilde Ij is 1. Okay, what is A tilde Ij? A tilde Ij is this guy. This is just simple calculation. This times this plus this times that, right? Now suppose you want a constant epsilon. Okay, so let's recall this regime again. We are in the regime when P is A times log n by n. Okay, so this was our dense regime, because this is the regime only where strong recovery is possible. Okay, remember there were two regimes, sparse regime and weak regime. Okay. Now if I take this P and plug it here and keep epsilon constant, then what happens? Then this guy goes to a constant which is 1 by e raised to power epsilon plus 1. Okay. Now here what it was? It was P. It was A log n by n. Okay. And so it turns out that if you work out the details, so the new graph essentially looks like so originally I had a graph n, A log n by n, B log n by n. Okay. The new graph has these parameters, n, a tilde log n by n, and b tilde log n by n. If you work these numbers out, a tilde and b tilde, they look like this. So a tilde and b tilde look like this. Now, a tilde and b tilde essentially increase by a certain formula, which is given by n by log n times this number. Now, what is this n by log n guy doing? N by log n is going to blow up. Okay? And a tilde and b tilde are essentially part of the connectivity probabilities. So previously, this was a log n by n and a was a constant. Now these numbers now start looking like a constant. Okay, so this a tilde log n by n will start to look like a constant, which is this guy. Okay. Previously, a log n by n was not a constant. Actually, this was going to 0 as n was going to infinity. So what's going to happen is this is going to densify the graph. So if the original graph had two communities and there was somehow some separation between the two communities, if you just apply vanilla randomized response, it's going to actually densify the graph if epsilon is constant. So what's the fix? You can still do recovery, but you need epsilon to grow. Okay. How fast does epsilon need to grow? It needs to grow as log n. So you can work the numbers out. You need to allow more leakage. So what is epsilon? Epsilon was our differential privacy budget. If epsilon grows as log n, then this algorithm does work and you can do recovery. But you have to suffer the price of privacy. But epsilon needs to grow logarithmically with the size of the network. So it works, but it's not so good in terms of the privacy budget. Okay. So input perturbation. So this was the first approach. Input perturbation is taking the graph, doing randomized response. It requires epsilon growing as log n, for example. So then the natural question to ask is, well, I still want to do exact recovery. I just want to hide the edge. Can I achieve a constant epsilon? Do I need to let epsilon grow with n? Why should I let the leakage grow? So then this leads to second approach of sampling this question.
Yeah, so originally, now we made some differential algorithm and now we got something E bar, and now we are trying to find out the original E from E bar, also we have the original. Why are we doing this?
No, we are not recovering A. We are recovering the label of the nodes. We are not recovering the graph. So you took the graph, you added some edges or deleted some edges, so you got a new graph. The graph is then passed to a community detection algorithm. Now every node is assigned a red label or a blue label. What is coming out from the algorithm is whether it's a blue node or a red node. Okay. So here's another very simple algorithm, Bayesian sampling. So what you do is you're given a graph G. For every possible sigma vector, you compute this probability. What is the probability that this sigma, or the probability of observing this sigma given the graph G? So you can write this as P sigma times Pg given sigma by Pg. And all of these probabilities we can compute in principle. And then what you do is you just sample and output a labeling with this probability. Okay. So, in some sense, what is this mechanism? This is a very simple mechanism. Just compute the posterior probabilities of the labels and then sample the label vector from these probabilities. We have done nothing as far as privatizing. We have not really added any noise. But surprisingly, the other mechanism gives some level of privacy for free. If epsilon is large enough, then this mechanism will still satisfy epsilon. If epsilon is large enough, if epsilon is smaller than a certain number, then we can't do anything. So specifically, if epsilon is greater than log of a by b, then we can actually get exact recovery. If a and b satisfy this lower bound, so the separation between a and b is greater than this. But anyway, this is not really a mechanism we would apply in practice. So this was sort of just an intermediate mechanism to motivate the real mechanism, which is exponential mechanism. Okay. So if I were to just draw, this is the non-private threshold. Okay. So below this is what was achieved before. Now the red one is what we get for this Bayesian sample. If epsilon was 2. Okay, so now all this was feasible without privacy, but now only this is feasible. This region is where recovery is possible. Okay, so the region where feasible recovery was possible has shrunk from all this to only this. Now, so Bayesian sampling required the knowledge of the graph statistics, because remember we are computing the posterior probabilities, and also requires epsilon to satisfy this condition of epsilon being greater than a by b. So can we overcome the shortcomings of the Bayesian method? Okay. So here is the exponential mechanism. What it does is, for every possible sigma vector, it computes a score. Score is essentially the number of, so let's say you have a label sigma. So sigma essentially defines a partition of the graph. If I red and blue, I can label the graph as red and blue, and then this defines a partition of the graph, and then you can look at the number of edges between the partition. Okay. If the number of edges is small, it's a good partition. If the number of edges is large, it's a bad partition. Okay, that's what I'm going to call a score. So for every possible vector sigma, you compute the score, which is the number of edges in the partition. If the score is high, you release it with a higher probability. Score is low, you release it with a lower probability. That makes sense. The probability with which you pick it from is e raised to power minus epsilon times the score. Okay? Does that make sense? Okay. So score is the number of edges between a fixed partition. Okay. So I have a graph. I have let's say a vector sigma defines +1 and -1. So I have blue nodes here and red nodes here. So I have some edges between. If they have more edges, is this a good cluster or is this a bad cluster? Bad or good? Somebody? Bad, right? So the more edges between the partitions is a bad cluster. So I should release this partition as my estimate of the community with low probability. Correct? So it should be inversely proportional to the score. So that's why I have e raised to power minus score. All I'm doing is just adding a factor epsilon there. And it turns out you can show that if you do sampling this way, you will also satisfy epsilon differential primes. So that's the idea. Yes, question. Size of the no, here you have to consider, I mean, so this is actually sampling over the entire set of possible partitions, so exponentially many.
All partitions are
correct. Score is just defined for every possible partition. Okay. So score function, you can show it's one link should satisfy edge-differential. So yes. So your question is, if I have but then the graph will not be drawn, so that graph will not be realized with a high probability either. So remember, so this algorithm is perfectly valid, there's nothing wrong in the algorithm as such, right? The question is about the utility of the algorithm. Okay? So the utility of the algorithm is driven by the underlying statistics of the graph. So the graph is balanced, half-half in each community. When you analyze it, if the graph is drawn with half-half, then this true realization will not happen with very high probability. So, yeah, all possible partitions. So every vector, so these are 2 raised to power n vectors. So L is 2 raised to power n vectors, basically. All vectors with plus 1 minus 1 entries. Right? So there are 2 raised to power n vectors. Every vector is assigned this probability, or proportional to this probability. You have to normalize it anyway. And then you're going to pick one with the, you'll sample from this probability distribution.
Yes, this question corresponds to, if I pick a partition which is somewhat balanced, I would expect the score as order n presumably. Because if I put here and I put here some order n number of edges.
Well, it depends. But the graph, if the graph is drawn from SBM PQ, P and Q are not the same, right? I'm not drawing graph on edges with probability half. The edges are being drawn from some natural SBM generated now. So if P is greater than Q, then the two community clusters will have fewer edges in between, depending on the separation between them.
So it's critical that your underlying set is L has to include all binary activity. You can't just restrict yourself to, because anyways you know that there are n by 2. Why would you output a clustering which does not satisfy that?
So that goes back to the worst case nature of the privacy notion that we settled upon. If we are willing to maybe relax that, then it might be possible to restrict yourself to instead of all the rest of our But does that answer your question? Sort of.
Yeah, I think
Sure. Okay. So here is what we get. This was non-private. This was Bayesian. So we better than Bayesian, we actually come quite close to non-private. So this is exponential. So exponential is a bit closer to non-private. Okay. Now, sampling methods, we are able to achieve pure DE, but they are not sufficient to implement because there are 2 raised to power n vectors to sample from. So, can we do something better? So here is my final mechanism. Hopefully give me 5 minutes and I'll be done. I don't want to take up more of your time. So here is the idea. Yeah, that question.
So the previous one don't even use A, B, nothing.
No. We don't
just
need
just look at scores.
Just look at the score. All you do is the score. It's a very universal, very flexible mechanism. If you want to use differential privacy for your favorite method or favorite, black box application as an example, all you need is the scores. So you have a function, you define a score function. The score function essentially tells you how good releasing a certain output is. Okay, so in this case 4 was the number of edges. All you need to do is prove Lipschitzness of the score function. Depending on the constant of the Lipschitz constant of the score function, you tune the scaling parameter of the sampling probabilities, and that's it. So it's a very nice tool. So we didn't do anything fancy. We learned about exponential and we applied it for this problem. Okay. So the next thing we did was we trying to improve upon exponential mechanism. So here is another mechanism called stability mechanism. So the idea is how stable is the estimator against edge modifications of the graph. Okay. So let's say I come up with an estimator, a community recovery algorithm, and if I change an edge, then I ask this question: how much does the output of the community labels change by changing one edge? If it is less stable, maybe I need to worry about privacy. If it is very stable, then maybe I don't. Okay. So if it is more stable, then it has less influence on the estimator, then it's more private. Okay. So the question is, how do we quantify stability of the estimator? So we can find that. So let's say I'm given a graph G, and I come up with an estimator sigma hat g. So sigma hat g is nothing but assigning blue and red labels to the nodes by looking at the graph g. Now, stability is, for us, we defined it as the minimum number of edges we need to edit. Okay, so that sigma hat, when applied on the edited graph, is not equal to the sigma hat on the ground graph. So essentially, how many minimum edge perturbations I need to do so that I change the output of the community detection. So this is what I call as d sigma hat g. It's just the minimum number of minimum k, such that there exists a g prime, the distance between g prime is k, and the output, then I apply the algorithm on g prime is not equal to. So if this is large, which means it's more stable. If d is large, which means I need to make more edits to change the output. If d is small, then it's less stable. Does that make sense?
This really applies to deterministic algorithms. The algorithm is maximized.
This definition itself is for a deterministic sigma. But then when we analyze it, we analyze it for algorithms with possible noise. And so here's a stability-based algorithm. In fact, this algorithm is also a classical algorithm. We didn't invent this algorithm. This algorithm was, if you know this old textbook on differential privacy, from Algorithmic Foundations of Differential Privacy by Goart and in one of the first chapters of that book, they also talk about this stability-based mechanisms. So what the idea is the following. So you're given a graph. You pick your non-private estimator, your favorite community detection algorithm. You get sigma hat g. Now what you do is you compute the stability of your algorithm. How stable is this algorithm? Or in other words, for us, how many edges do I need to perturb to change the output? Now, computing this guy itself will potentially leak information because you're touching the graph. Okay, computing stability of a function for a fixed graph g also looks at the graph g. So which means you are leaking something. So what we do, or what actually this algorithm does, is it takes d, computes d in a vanilla form, and then applies noise on the estimate on d itself, and then computes a private version or private estimate of the stability itself. Okay. So you have to be careful when you do these steps, so that because information leakage can happen at any stage. So every step has to be privatized. Okay. So we estimate, or privately estimate how stable my estimator is, my community detection estimator is. Once I estimate this, then I do the following. If it is greater than a certain threshold, if it is larger than that, then it's very stable. Then I release it. Yes, let me just release this thing as it is. If it is less than this, then I say it is not stable enough. I'm going to just flip points and release a random value. Okay, that's the algorithm. Right? And one can show that standard analysis for any community detection algorithm, this algorithm satisfies epsilon, comma, delta, edge-differential. So all this in itself is pretty standard. The hard part was to analyze this algorithm. So that's where we did a lot of work to analyze this algorithm. So we analyzed this for the maximum likelihood estimator, and showed that we get very similar flavor of results as was done for Abe and Moselle, the classical results. So remember, their threshold was square root a minus square root b is greater than square root 2. Right, if you remember, so forget this edit multiplicative term from here. This was Abe's threshold, non-private. What we get for epsilon delta differential privacy, we get a multiplicative term. So this difference between A and B has to be more. How much more? A multiplicative factor more by this much amount. Square root of 1 plus t plus 1 by 2 epsilon. Epsilon, remember, is our privacy packet. As epsilon increases, this term goes to 0, or not goes to 0, becomes 1, and then we go back to the classical non-private threshold. This delta is, we pick as n raised to power minus t, and then of course as t increases, then of course also the current goes. And then since maximum likelihood estimator, remember, was also NP hard, so we said, well, let's see, can we analyze SDP relaxation of NP, and so we did that. So we pay a little bit of price, so we get a slightly worse threshold than maximum likelihood, but then this runs in quasi-polynomial. Okay, so
So, do you also, this kind of suggests that if you move towards pure DP, taking T larger,
no, T small, T larger.
then the required gap between A and B starts going up.
Starts with.
So, is there a pure DP not feasible?
We don't know. No, pure DP was feasible with exponential mechanism. So exponential mechanism was giving us pure DP. But now we can go even closer to that line, but we give a slack of delta. Okay, so we give a slack of delta, so we relax the privacy notion, but we move closer to the threshold. So analyzing this, there were two sources of error. I guess due to interest of time, I'm going to skip this. Bottom line is we need to show bounds on the stability of the estimators, that how stable they are. So the able showing maximum likelihood is roughly requires log n edges to be linked to change the maximum likelihood estimator. That's sort of the core of the proof. Right? Let's skip this. So if you see what it looks like, so this was a non-private threshold. This was Bayesian, this was exponential, and now you can actually come even closer with the stability mechanism. So we get better than exponential, but of course we pay the price of delta. We did some real world, it's customary now, ICML, ICLR, we have to add some simulation results. So students pick two data sets. There is this Zachary Karate Club. It's a very simple, small data set of 34 members of karate club, some university in the 70s. And there's a political block data set, older data set from 2004 elections. So we ran the algorithms on these two data sets. And what we saw was sort of interesting and conforming to our theoretical results. That if you look at, so let me pick, let's say, this one. So this is the political block data set. And the x-axis is the privacy budget. Okay. So as epsilon grows, we expect, we are aligned to leak more. Y-axis is the probability that sigma hat is not equal to sigma. So when this error go down as epsilon grows. Randomized response starts pretty high. Okay. So we did randomized response and then did SDP, community recovery on top of it. So it starts high and then goes down and then goes to 0, but goes down way later for larger epsilon. SDP and stability for delta being 10 raised to the power -3 goes down much faster. So we observed this both in the theory and some of our basic examples. And the full paper is available on archive and published last year. No, the SDP is just the relaxation, the algorithmic relaxation. Okay, so just to conclude, we studied this problem of community detection subject to edge-DP. We basically analyzed three privacy preserving mechanisms in a nutshell. We started with the most basic one, randomized response, and then sampling and stability based ones. Very interesting interplays between three core aspects: privacy, efficiency, utility, and recovery of the communities. I must say there are many interesting problems. We haven't studied weak recovery. So weak recovery, of course, people have studied with a lot of potential. That's wide open. Other random graph models, overlapping communities to be connected, SBMs. SBM, what we studied, which is basic. It's unclear whether overlapping communities will may not help us from detection, but may help us from privacy. Because if you have overlapping communities, maybe hiding edges is easier perhaps. So that's interesting angle filtering to be explored. Converse bounds, this is probably the most interesting for me. How the Abe and Moselle did the converse, they just analyzed the like some likelihood estimator. We don't know what's the analog of that argument. So we don't know whether what is the optimal private maximum likelihood. There is no such thing within our context. So this is perhaps the most intriguing question. Thinking about converse bounds. So I think that's all I have to say.
Okay, it's time for